In 2009, this paper reported that 75% of patients hospitalised for heart attack did not, in fact, have high LDL. Which leads to the question, if LDL doesn't cause heart disease, if it doesn't cause these atherosclerotic plaques, what does? Do we have a better alternative? This, a blood clot. I'm going to argue that your risk of clotting is a key risk factor in both developing atherosclerosis and dropping dead of a heart attack. The role of blood clots, which can be called thrombosis, in causing heart attacks is both well known and accepted. Fatty-looking blockages like this often exist without any symptoms at all because there's still enough room for the blood to get past. A complete occlusion, however, as can be caused by a thrombosis or a blood clot, is a different story. Look on the right at the thrombosis. You can see it's filling the space where blood once flowed. In the wrong artery, this could easily prove fatal. What is less well known, however, is that these blood clots actually cause atherosclerotic plaques to form in the first place. You see, atherosclerotic plaques are basically healed blood clots. After a thrombosis or blood clot forms, it heals, but it does not completely disappear. And repeated episodes of thrombosis over time leads to the progressive build-up of a plaque. Here, you can see a single plaque with the lipid or cholesterol core covered by a layer of connective tissue. Compare that to this example with two layers of plaque, one on top of the other. The more recent thrombosis is sitting on top of an older one. In fact, this cyclical process can occur as many as 4 times at a single site within an artery. This still leaves us with the question, though, of where do these crystals, these elongated shapes that we see in atherosclerotic plaques, come from? It's been long accepted that they're made of cholesterol, which is released by LDL particles contained within these bulbous structures here called foam cells. The foam cell that you've just seen are formed when something called a scavenger receptor on a macrophage or a smooth muscle cell binds to a damaged LDL particle and ingests it. These foam cells then store the cholesterol bound with fatty acids in droplet form. Now, foam cells don't like to release this cholesterol. That's what makes them foam cells in the first place. It makes it hard for them to contribute to cholesterol crystals. As you know, there's a big difference between a droplet and a crystalline deposit that you see in atherosclerosis. To make the crystals, you actually need pure cholesterol. What then can provide the ingredients for these crystal shapes that we see in atherosclerotic plaques? And red blood cells is the answer. Their outer membrane contains more free cholesterol than any other cell in the body. And not surprisingly, red blood cells are quite abundant in blood clots. And when we look within atherosclerotic plaques, we see clear evidence of these blood clots. We see the presence of platelets, which are fragments that play a key role in initiating blood clotting, and we see fibrin, which forms fibrous strands that binds it all together. This study, for example, surgically removed sections of atherosclerotic plaque and found clear evidence of all of these ingredients deep within. They obtained further definitive proof of the presence of red blood cells by using a brown stain for a chemical called glycophorin A, a chemical only found in red blood cells. Look at all the brown. Conclusive proof of degraded red blood cells deep within a plaque. It clearly describes the central accumulation of red blood cell membrane within atherosclerosis. Furthermore, the investigators also injected red blood cells into animal models of atherosclerosis and found that this blood injection produced plaques containing both cholesterol crystals and foam cells. The upshot of all of this is that thrombosis, or blood clots, are central to the development of atherosclerosis. And so, clotting risk, what we call a procoagulant tendency, must too be a risk for atherosclerosis. So this raises the question, how do the lipid risk factors for heart disease that we all know about relate to clotting tendency, if at all? Now, you may have seen one of my previous lectures where I talk about the validity of triglycerides and HDL as markers of cardiovascular risk. Essentially, there's robust evidence that high triglycerides and low HDL is associated with an increased risk of heart disease. So I began to explore whether these metrics had any association at all with the risk of blood clotting. If they don't, then this whole clot theory goes down the drain, except they do. And I didn't have to look very far. Literally dozens of papers have been published on these connections between lipid parameters in the blood and clotting risk. For example, triglycerides associate with the activity of factor VII, a key component of blood clotting. HDL inhibits the clumping of platelets, a key initiating factor in the formation of clots in the first place. Therefore, a low HDL level removes the brake on clot formation, and oxidized LDL promotes both platelet clumping and also the secretion of something called tissue factor, the single most potent stimulus of clotting there is. Whatever way you look at it, what we consider to be lipid risk factors are in actual fact clotting risk factors. A high triglyceride level or a low HDL level is an independent risk factor for thrombosis. Now, the risk of thrombosis, or these blood clots, is manifestly increased when a plaque ruptures. Fortunately, plaques are often stable, and here you can see one such example. The yellow arrow points to a relatively thick margin of connective tissue lying over the top of a plaque. This, on the other hand, is an example of an unstable plaque with only a thin layer of connective tissue over the top. Which leads to the question, what causes thinning or destabilisation of this protective cap? And one answer is foam cells. Those cholesterol-stuffed macrophages you saw earlier, they can secrete enzymes that break down the protective tissue cap. These enzymes are called matrix metalloproteinases, and high levels have been independently associated with the tendency of plaques to rupture. There's 23 different types of matrix metalloproteinases in humans, and one which has been consistently shown to play an important role in plaque rupture is number 9. In fact, high levels of matrix metalloproteinase 9 has been shown to be an independent predictor of cardiac mortality. Which led me to ask the question, do triglycerides and HDL levels have any association with matrix metalloproteinase 9, given it plays a key role in cardiac risk? And not surprisingly, the answer is yes. Both high triglycerides and low HDL is associated with plaque destabilising matrix metalloproteinase 9. And more specifically, oxidized LDL, the presence of which is indicated by a poor triglyceride to HDL ratio, has been shown to play a causal role in matrix metalloproteinase 9 activity. Of course, there's other factors that are key to the formation of a blood clot besides unstable plaques. And one of the most important of these, perhaps, is damage to the inside lining of blood vessels. Here you can see hair-like structures lining an artery, and this is what is called the glycocalyx, and it's the first line of mechanical protection that arteries have against clotting. Amongst other things, the glycocalyx shields the artery wall from coagulation particles. It secretes a protein that blocks abnormal clots from forming called antithrombin 3. It mediates the production of nitric oxide, which dilates blood vessels, and itself is another potent inhibitor of coagulation. In short, the glycocalyx is an effective defence against coagulation and against thrombosis. It should be no surprise then that oxidised LDL can damage the glycocalyx. And once this barrier of protection is gone, the risk of thrombosis increases exponentially. Now's a good time to get to one of the key root causes of heart disease: oxidation. Oxidation is basically an umbrella term that refers to a chemical reaction that occurs when an electron is torn away from a molecule or atoms. That's basically what rusting is. And oxidised LDL and other sources of oxidation in our blood can do this to the proteins and fats within our blood vessels. You've probably heard the term free radical. This is a term we often use for molecules that can cause this oxidation damage. Oxidation itself is bad. Non-oxidised LDL is perfectly fine. Any source of oxidation stress within our blood vessels can damage the lining of our arteries, damage the glycocalyx. It just so happens that LDL, being a normal resident in our circulation, can be a very effective vehicle of oxidation, but only if it is oxidised. That oxidation itself is a major cause of heart disease, and I do deliberately use the word cause, is why antioxidant supplements like N-acetylcysteine have been found to be protective against heart disease. The fact is, any source of oxidation which enters our circulation is bad news. And that includes what we inhale. After President Eisenhower's heart attack, his doctors probably shouldn't have overlooked his 2 to 3 pack a day smoking habit, because that was almost certainly a major cause. You see, the pollutant particles that we inhale, including from smoking, can enter our circulation, a fact that was proven more than 20 years ago. And within 1 minute of inhalation, this particulate pollution is detectable in the blood. And these particles carry with them oxidation stress. And this is why there is such a strong relationship between pollution and cardiovascular mortality. And what about diabetes? After all, we know that diabetes is associated with a tripling of the risk of dying from heart disease and stroke. Well, it comes down to sugar in the blood. Consider this research from 1962 that demonstrated blood glucose abnormalities occurred in 73% of heart attack patients. This has been known for a long time. And the mechanism? Oxidative stress. It's been long known that high and fluctuating blood glucose levels, as occurs in diabetes, generates this oxidation. Which is one reason high blood glucose levels increase clot risk. Yes, we're back here. High glucose levels also stimulate matrix metalloproteinase 9 secretion. Remember that plaque destabilising enzyme? Here you can see both type 1 and type 2 diabetics have much higher levels of this plaque destabilising enzyme in their aortas. Because of their polyunsaturated structure, characterised by a readily reactive double bonds, these oils are very prone to oxidation, even without cooking. This study found high rates of oxidation within walnut oil occurred within days, and consumption of oxidised oil leads to oxidation of lipoproteins within our blood, lipoproteins that can deliver oxidation stress throughout our arteries. Compare the blood oxidation levels after consumption of a low oxidised oil to that of a highly oxidised oil. Understand that oxidation within our circulation is a cause of heart disease. And if you understand that, you can see why seed oils could be a problem. You see, they contain something called phytosterol, or plant sterol, which you can think of as fake plant cholesterol. As you can see, they're near identical to cholesterol, but not quite. Similar enough to be absorbed by the body in place of cholesterol, but different enough to not work the same. Basically, phytosterols interfere with the normal biochemical processes that use cholesterol. The highest concentration of these plant sterols is found within seed oils, especially rice bran, corn and rapeseed. And another significant contributor of these plant sterols in our diet, simply due to the volume consumed, is cereal. And while our body tries to reject plant sterols, some does get through. About 1% of what we consume actually gets incorporated into our tissues. And one of the tissues this fake plant cholesterol gets into is your arteries. And it's probably no surprise that when it does, it's associated with premature, severe cardiovascular disease. Proof of that was provided when researchers performed a biopsy of the aorta of a 33-year-old male with premature severe cardiac disease and detected plant sterols. And this is not an isolated finding. These 3 papers from 2005, 2011 and 2015 all reported plant sterols were detected in diseased arteries. Interestingly, it's likely that these plant sterols also contribute to the crystals found in atherosclerosis. They may not, in fact, be made of cholesterol. Understand that you're not looking here at crystals directly, but rather the space where they used to be before they were dissolved in processing. And it's entirely possible, and I would argue likely, that one source of these crystals is phytosterol or plant sterol. You see, being almost identical to cholesterol, plant sterols readily form crystals which are difficult to differentiate from those formed by cholesterol. Remember these foam cells, the supposed supply of cholesterol? Well, while foam cells don't like to release their cholesterol, they're only too happy to spit out phytosterol or plant sterols. This makes phytosterol a much more likely contributor to these crystals. Observe how foam cells or macrophages are only too happy to store cholesterol compared to plant sterols. And plant sterols, which may form these crystals, might also be supplied by degraded red blood cells. For not only does the outer membrane of red blood cells contain more free cholesterol than any other cell in the body, it also contains plant sterols. The consumption of plant foods, especially seed oils, has been repeatedly shown by research to result in plant sterol accumulation within red blood cell membranes. Interestingly enough, at the expense of cholesterol. And I think it's very likely that through oxidation stress and plant sterols, seed oils are quite possibly an even more significant cause of modern disease than are carbohydrates and sugars. This paper, for example, after analysis of over 195,000 subjects, concluded that seed oil intake resulted in a greater incidence of death than sugar when it exceeded 6% of energy in the diet. Consider then that the average Australian gets more than 13% of their energy from seed oils. And when we look at the intake of polyunsaturated fat, which is a very good surrogate for seed oil intake, we can see consumption began to rise in the early 1900s, well timed to have a causal role in the epidemic of heart disease that followed. Which is why 3 large-scale randomised controlled trials, the gold standard of research, have found that replacing saturated fat with seed oil led to a significant increase in mortality. And to my knowledge, there's no study that shows otherwise. Ongoing review of data from the Women's Health Initiative, for example, a study of over 48,000 females, has found that lowering saturated fat intake is associated with an increased risk of heart disease of between 47 and 61%. Findings of another study based in Sydney, which ran between 1966 and 1973, were finally disclosed in 2013, reporting that replacing saturated fat with polyunsaturated fat in men who'd had a heart attack increased their subsequent risk of death by 62%. And in a very similar story, the mortality data from the Minnesota Coronary Survey, which was completed also in 1973, was not published until 2016, and when it was published, it revealed that in a population of 7,000 participants, increased seed oil intake increased the risk of death. The plant sterols within seed oils also plays a role in reducing blood levels of LDL. It does this by inhibiting the normal, healthy absorption of cholesterol from the small intestine that leads to a reduction in the production of the LDL precursor, VLDL, and it also increases the removal of LDL from the blood. And this combined LDL lowering effect of plant sterols is why increased saturated fat intake seems to raise cholesterol. You see, saturated fat often comes from animal sources. That means it doesn't contain plant sterols. And if you reduce your seed oil intake while you increase your animal fat intake, your cholesterol levels may be permitted to return to normal levels. Not go high, because saturated fat's not making it go high, but it's the removal of the seed oils that's permitting the LDL to rise back to normal, healthy, physiological levels. There's one major exception to saturated fat intake being associated with increased LDL, and it's the exception that proves the rule. That's coconut oil. Coconut oil is a plant oil. It contains sterols, and that's why coconut oil drops LDL levels, while at the same time loading your body tissues with plant sterols. Indeed, this knowledge makes me reconsider whether coconut oil is actually healthy. As you may know, in high-risk populations, that is in subjects with heart disease, statins have been shown to reduce the number of cardiac events. And the mechanism behind this has nothing at all to do with lowering of LDL. Rather, statins inhibit blood clotting pathways and inhibit the release of plaque destabilising matrix metalloproteinases. Inhibition of clotting can also have complications. This is clear with the significant increased risk of brain bleeding known as hemorrhagic stroke that occurs with statin therapy. The side effects, however, which include a 71% increased risk of developing diabetes, are likely to attenuate this benefit over time. And perhaps this is the reason why the only study that appeared to show a mortality benefit of statins in a primary prevention population was terminated early. By being a shorter trial, perhaps the full impact of statin side effects was attenuated. I'd like to acknowledge the work of Scottish GP Malcolm Kendrick on exposing the role of blood clots in atherosclerosis. This is well documented in his book, which provides an excellent summary of the clotting theory. Still, I wouldn't be surprised if you'd never heard of him, because he's a fringe figure who had the outrageous audacity of arguing against the lipid hypothesis. As a result, he's been cancelled. That's the justification that was provided for the deletion of his Wikipedia page. The whole story we've been fed about saturated fat causing atherosclerosis is nothing but a big old fairy tale. Rather than worrying about how much saturated fat we're consuming, we should be worried about factors that increase our clotting risk, like oxidation, pollution, seed oil consumption, and blood glucose levels.